So real-time audio in Python. First, a disclaimer. I'm a researcher at Technical University of Vienna, so I'm not really an audio professional programmer. And also, as you probably know, Python has its limitations when doing real-time audio, so keep that in mind when using this package or also during the presentation. So first, a few references to existing Python packages. There's Popsicle, which are the juice bindings for Python. And the last commit was in 2024, so it's not really maintained as far as I know. And another interesting high-level package is also PyO, which has a full C backend and only Python front-end functions to basically assemble this fast C-coded audio backend. And then there are functions for accessing the sound device or audio interface directly. There's the sound card library in pure Python, and then there's mappings for the port audio library, sound device, and PyAudio. And sound device is the actual package asmu uses in the backend to do the communication with the audio device. So what is asmu? Asmu is a high-level package for doing real-time audio. And the idea is that you have a high-level structure where you just connect up blocks, which we will see in a minute. And the user does not touch the audio itself, except you want to develop blocks for asmu. And standing out point is that it has a pure Python back and front end, so no other program languages required. You can program back and front end in pure Python. There's already many features implemented. So we have many blocks, which I will go through later. You can do calibration handling. The calibration is stored in the JSON format. You can load and save calibration data, which is very handy for acoustic measurements. There's documentation available. And right now, it's a quite compact code base. So if you get started now, it's easy to pick up. And it's platform independent, so it even runs on a Raspberry Pi. And of course, we have the problems related to Python. So because Python is an interpreted language, the operating system can anytime decide to interrupt your process. But in practice, this did not really happen to me. So just keep it in mind when you use it. Don't use it for critical applications. And with Python, there's also some careful development required because you don't want to allocate memory, of course, in the real-time environment. And you want to have fast execution times. So with Python, there's not much documentation out there on the function if they allocate memory in the back. So we have to do some profiling, which I will also mention later. So to get started, it's quite simple because asmu is hosted on the Python package index. So you can do a pip install asmu, or you can get fancy and do the interactive installation if you want to develop or look into the code. Then you scan your devices. This is basically a port audio call. And then I would recommend to study the documentation, look at some examples, and get started using asmu. I will also present some small programs or applications today. The first one is the Hello World of audio software, playing a simple sine wave. So this is the beginning of the code. So we first import asmu and the time module. Then we create our blocks, and the most central block is the interface block, which does all the audio interface communication. And we need a sine generator, of course. A generator block is, in general, a block that has only outputs. So in this case, we instantiate the sine block with a frequency of 250 Hertz. Then we connect them up. So in this case, I opted for a stereo setup. So we have two analog outputs of the interface on channel 1 and 2. And we connect this single sine output to both of them. And finally, we can start the audio stream, wait for 5 seconds. And if you run this, you should hear a 5-second sine wave. And this can be run quite easily with the normal Python interpreter, no special environments or dependencies required. So this should work right away. So this is the basic high-level structure, which you will use as a user. So we have the top module, the asmu package, which has the A setup class for handling the configuration and calibration setups. Then we have the A file class, which does the audio file handling, and the interface class, which you've seen before. And then we have some submodules. As I mentioned, these are these blocks you will shuffle around and connect to do your setups. We have the generator blocks like a player to play an audio file, a sign generator, noise generator, and so on. You have different effects, which are blocks with inputs and outputs. A summing effect, of course, a gain ramp, which allows you to dynamically ramp the gain up and down. We have weighting effects, for example, for A weighting. And the analyzer blocks are blocks with just inputs, for example, FFT, record to a file, RMS averaging, and stuff like this. And the optional imports we will discuss later. So another application. So this is an application from my PhD research, which is a development of a low-cost microphone. And in that project, we developed a microphone you can build for 10 euros. Material costs, and we built 50 or more of them. And we wanted an easy setup to calibrate them, store the data, do some calibration sheets. And this is where this package and this full Python workflow came in really handy, because we did the measurements using ASMU, and then we had all the data in Python and could access via Python. And this was very easy to then do the database integration, generate some automated calibration sheets using LaTeX. And if you're interested, you can look this up in the publication. And this was done by comparing a signal of a reference microphone from a Brüel & microphone to our device under test in this soundproof box with a speaker excitation. And the code for this is quite simple. Of course, this is a simplified example, but just to walk you through, we again import our dependencies, so ASMU, of course, and then we want to have a plot of the frequency response of the microphone. Then we create our blocks again. This time I'm specifying the specific audio device and a higher sample rate. We need a noise generator and an FFT. Then we connect them up. So the noise generator should go to the audio interface output, to the speaker, and then we want the audio interface inputs on channel 1 and 2 connected to the FFT block. And here I just marked that channel 0 of the FFT is the reference, and channel 1 of the FFT is the device under test. Finally, we can run it, and this command will block until we get one full FFT, and per default, this is a 1 second measurement. And then we can just plot it, compute the transfer function, which basically dividing the two NumPy arrays. And yeah, here you can, if you would run this, you would see a plot of the frequency response. Of course, in reality, there's some more averaging, some advanced filtering happening, but this is the most basic example of how to measure the frequency response to a known reference. Another example from a different context, not measurement, but more artistic, was an art diploma called the Music in Carpet. And there we wanted an interactive carpet, which basically controls a multi-channel audio installation. And the carpet you can see in the picture on the right was fitted with custom pressure sensors, which then put out the pressure data to the PC. And there we used ASMU to dynamically adjust the volume. And again, some small code example. Here we define the paths to the audio files used for the multi-channel installation, and just as a placeholder, it's apple, beer, and C. Then we have our blocks again, so we need a central interface block. We have a summing bus, which we'll use to sum up all the audio channels. And the summing bus's output is connected to the interface output on channel 1, which would be a mono setup in this case. And then we allocate some empty lists and start a loop over this file path list. And in this loop, we can parametrically assemble all the blocks. So in here, we generate an A file object. We open the file and store it in the list. Then we generate this player generator, pass it the A file, and then we have this gain ramp effect, which we can use to in real time adjust the gain of the player. This is also stored in the list, and then we connect everything up. So the player is connected to the ramp input, to the gain ramp, and the ramp output is then connected to the summing bus. And the beauty of all of this is that it's really truly parametric. So if you want 10 channels, 50 channels, you want different paths, you just change line 3, you just change the paths to the audio files, and when you run it, everything else is assembled and connected automatically. And of course, we need to run it. So this time we start the stream a little bit differently. So we start the stream first, and then we have this try accept statement. And in there we have an infinite loop where we enumerate over the gain ramps we stored in the list previously. And then we get the sensor measurements from the carpet of each channel and set the gain for the gain ramp to, in real time, update the gain. So this would be the real-time loop, which would happen in the front end basically, and the back end is doing the audio processing in a different thread. Yeah, and if you do something like this, where you have a stream started like this and some files open, don't forget to clean up in the end. So in this finally statement, we stop and close the stream and close all the open files. In the second half of the presentation, I want to dig a bit deeper in how asmu works behind the curtains or behind what you've seen until now. So we have some optional imports, or basically the module structure we use in the backend. There's the processor class, which is basically the parent class of the generator, effect, and analyzer blocks. Then we have the I/O class, which holds the input and output classes used for connecting things up and storing calibration data. The A-core submodule holds the small size audio classes that do all the audio processing in the backend. So also quite important submodule. And then we have some advanced typing and exceptions, which is not super interesting right now. So one class structure example, so you can imagine how all of these different submodules work together to enable real-time audio. So I talked about the parent class, the processor, and inherited from that we have the generator, which is, of course, has some outputs. And these outputs is a list of basically output class objects. And then we can inherit from this general generator class, for example, the sign generator. And there we connect this basically front-end user interface inside Python to the audio core that has to run in real time, of course. And there's the equivalent of the generator, which is the part the user touches. We have an A generator, and this is the small size backend class housed in the A core submodule where we do the actual sign computation. And of course, the interface is also a port processor, which is the central part. And here we have some derived fancy interface inputs and interface outputs, which can store additional calibration data, channel name, stuff like this, which can also be loaded and stored in the JSON format. And also this interface has an instance of an A-core object called A interface. And here is the most important function for real-time audio, the callback function. And this is called by port audio regularly and has to hit the strict timings to enable real-time audio. And how this works, the audio backend, I want to show you on this slide. So in this small example, we have this A interface, A core class, which has this callback function. And now we want to do a simple sign generator. And our goal is that we end up with a sign in this out data buffer, which is given to the callback function. And how I do this is in asmu, we do on-demand computing. That means we don't compute or allocate this stuff beforehand in different threads or something, but we go up this row of connections against the audio stream. That's why all the functions are called upstream. And we pass on basically this callback call on upstream against the audio stream until we reach a hard end, in this case a generator. And then this reference, this on-passed reference for the out data is written to by the generator. So this should not, in theory, not allocate memory. And then this function returns. And then we can do the processing all on the same buffer. So in theory, this concept works without allocating any memory and works quite efficiently in Python. And the other way around, if we want to get some live data from the interface and then pass it on to, for example, an FFT, we also choose the route of going upstream, again, against the audio data. So the interface knows all the instances of A analyzers, and the A analyzers have a function called start upstream. This again passes this call fully upstream until it reaches, again, in this case, the interface. Could also be a generator if no interface is involved. And then again, we copy this in-data buffer to the out-data or just pass the reference. Then we can apply, for example, here again, simple multiplication. And finally, we can apply the Fourier transform to this out-data buffer. Yeah, and as I mentioned at the beginning, programming time-critical stuff and memory-critical stuff in Python is quite hard. So I extensively use profiling to check what the functions do in the background and how to set the arguments properly to get them as fast as possible. For example, here is the numpy.sign used to generate the sign in the outdata block, and this takes 20.9 microseconds. So this is quite good execution time for hitting like a 1 millisecond goal. And for example, the memory profiler, here something odd happens. So although we specify a pre-allocated reference buffer, the numpy.sign function still allocates some memory. And this is something that unfortunately cannot be avoided because some of the functions do something in the back and still allocate some small amounts of memory. And this is something to watch out for when you do such blocks for the asmu in the asmu framework. And finally, some words on testing. So asmu is hosted on GitLab and also in the Python package index, and we have some automated integration testing through the GitLab CI pipeline. We have integration tests where we test some blocks connected together, like, for example, testing the FFT block with a sine wave or vice versa. Then we do automated benchmarking of the callback function. So for these integration tests, there's also a benchmarking happening on the callback function for each commit. So we can see if some code changes broke something or slowed something down significantly. We do coverage testing. Right now, I think it's at 85%. And new is now also unit testing to really isolate the different blocks and see if something breaks very specifically. And in the future, we want to also run some hardware testing via a local GitLab runner. So finally, I want to remind you of the 3 most important words of this presentation. Pip install asmu. Try it. It's fun. Then there's the logo and the link again. And big thanks to all the dependencies. asmu has to use a few dependencies to keep this fast execution happening, especially PyFFTW, the Py mappings for the FFTW library really sped up the FFT processing. And yeah, if you have any questions, just drop me a message on Discord or contact me via the contact details. Thank you.